So let's continue with equivalent matrices. And so in this video as well, I am going to do the lecture and the tutorial together. Okay, so it might be a bit long. Okay, so let's continue. Definition and recall. We are still in yeah, okay, so if you want I can we are still in section 4. Okay, and part B, in section 4, part B. So let me write it down. We are still in change of basis. Okay, and last time we started section B, which was changing map representation or representations. Changing map presentations. Okay. So last time we have seen how to represent a map in a different pair of bases. Okay, with respect to a different pair of bases, and I have shown you the diagram. Okay, so today we will continue with the number 4. Okay, we have done number 1, 2, 3 in the previous video. We will continue with the number 4. So let's start with the definition. Excuse me. So same sized matrices H and H hat are matrix equivalent matrix equivalent if there are non-singular matrices. There are non-singular matrices P and Q, okay, such that H hat, okay, let me write it in green as well. This is important formula, such that H hat equals P H Q. And okay, where does the P and Q, where do the P and Q come from? If you remember from the previous tutorial, lecture and tutorial, we have seen the following diagram. So let's say our function h is defined from V to W, okay, and from V with respect to a certain base B, and to W with respect to a certain base D. So this is our map H. The matrix representation of that map is big H. Now let's say we want to represent that same map from V again to W, but this time with respect to a different pair of bases. So this time from V with respect to a basis called B hat, and to W with respect to a basis called G hat. Okay, and we have also seen that from B to B, uh, from V to V, B to B hat. Actually, the map we have the identity map. Okay, we have seen how to represent a vector with respect to a different kind of basis, and we have seen that since the vector is not changing, but its representation is changing, the underlying map is the identity map, because the identity map doesn't change the vector. Okay, and here as well from W to W is going to be the identity map. And when it comes to uh, the map from V with respect to B hat to W with respect to D hat, we still have our map, our same map, but this time the representation is going to be different, H hat. And we have seen that, or I have explained that to get a H hat, what we can do is to go up. So we go up, let me change color. To find a H hat, we go up, across, and then down to find H hat. So we have a H hat, okay, which is the representation, okay, of H with respect to B hat, G hat is going to be equal to, we go up, the representation is going to be equal to the, let me write it, it's going to be equal to the representation of the identity map with respect to B hat, B, with respect to B hat, B, okay, multiply, so that's up, now across, we have H, multiply by the representation of the identity map with respect to G hat, G hat. So as you can see, so this is our H hat. We can see we can derive the fact that our P, this is P, H, and Q. Okay, so we have our H here, H hat here. So that means our P, so this means the P, the non-singular matrix P, is equal to the representation of the identity map with respect to B hat, B, and the Q we are looking for is the representation of the identity map with respect to G hat. Is that okay? So this is just um, the definition of what we have started saying from the previous video, so in the previous video, we have seen how to find the H hat, and in this video, when we have the H and H hat, the two matrices represented the same map, but with respect to different pair of bases, then those two matrices are known as being matrix equivalent. Okay, so if you are asked to find H hat such that H and H hat are matrix equivalent, you just have to remember this diagram and find those P and Q, which are the representations of the identity maps. Okay, so let's continue. Number 5, corollary. Okay, matrix equivalent. Okay, matrix equivalent matrices. Okay, represent, of course, they do represent the same map with respect to appropriate pair of bases. With respect to appropriate pairs of bases. Okay, that's what I have saying, as I have been saying. Number 6, theorem. Okay, so here we have any m by n matrix of rank k is a matrix equivalent to the m by n matrix that is all zeros except that the first k diagonal entries are ones. Okay, so here is what is known as the block partial identity. So this is what I mean. So we have, let's say we have 1 0 0 1 dot 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 0 0 to that's one dot 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 0 0. Okay, dot 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 0 0 0 0 1 0 0 0. Okay, 0 0, and we have we are going to continue with the 0 0. Okay, 0 0, and I will do a tutorial very soon so that you can see. Okay, so this is known as this is known as a block partial identity. A block partial identity. Okay, why? Because we say there so the matrix is all zero except that the first k diagonal entries are ones. Okay, this is entries, not this is entries. Entries. So from there, okay, so there, maybe let me change color. So here is the k diagonal entries. So here is the k diagonal entries. Okay, they are one, and the rest is zero. Okay, so this looks like we have the identity there: zero, zeros, and zeros. Okay, so you can split these methods into four if you want to. I can continue with this, as you can see. Okay, so we have the identity here. The identity is there. This matrix is 0, this is 0, and this is 0. Is that okay? This is known as block partial identity, and we have said that the theorem says that any matrix equivalent um, is any m by n matrix of rank k is matrix equivalent to any m by n matrix uh, block partial to any block partial identity matrix that is m by n. I hope you get it. So basically, any matrix, any m by n matrix is equivalent to a specific block partial identity matrix. So the block partial identity matrix is known as the canonical form of matrix equivalence. Okay, so let me continue on next page. Okay, this time is going to be corollary. Okay, matrix, equivalence classes are characterized by rank. Characterized by rank. That is, or that means two same size matrices are matrix equivalent if and only if they have the same rank. Okay, so we are going to finish the lecture with the following notes. Number 1 here. Matrix equivalence is a generalization of row equivalence. Okay, matrix equivalence is a generalization of row equivalence. Okay, number 2. Two matrices are row equivalent if one can be converted to the other by a sequence of row reduction steps. Okay, Gauss elimination or Gauss Jordan. So two matrices are row equivalent. Okay, if one can be converted to the other by a sequence of row reduction steps. Okay. And two matrices are matrix equivalent if one can be converted to the other by a sequence of row reduction steps followed by a sequence of columns reduction steps. This is important, very important. Two matrices. Let me write it in different color because we are going to use this for the tutorial. So let me write it in black. Two matrices matrix equivalent if one can be converted to the other by a sequence of row reduction steps followed by a sequence of column reduction steps. So I hope you get what I mean here. You remember when we did Gauss elimination? So we started with a matrix, and then we do some row reduction steps, and we get to the echelon form. Okay, something like that. Okay, even if it's not the final echelon form. Okay, so we can say that the original matrix and any intermediate matrix, okay, while performing Gauss eliminations, those matrices are row equivalent because we got from matrix 1 to matrix 2 by a row reduction steps. Okay, and if you remember, that is a Gauss elimination. Okay, but when we did Gauss-Jordan eliminations, we went to few steps further to be able to get the, so we didn't stop here. So from here to there, we did Gauss eliminations. And from there, we got to be able to get the identity. Actually, it was block identity metric, block partial identity matrix we got. Okay, so basically when we did Gauss-Jordan eliminations, what did we do? We got all ones, okay, in the diagonal matrix, and the rest is 0 0. Okay, if you remember Gauss-Jordan. So from there to there, this time we can do columns. This is row reductions, okay, to get the echelon form. And to be able to get the reduced echelon form, what we are going to do this time is we can do columns reductions. Okay, so I think I should give myself enough space here. So to get to this is echelon form. We do Gauss eliminations. Now to get to the reduced, so yeah, let's have something like this. Okay, to get the reduced echelon form, what did we do? what this note is telling us is we can do actually column reduction. Okay, here using Gauss Jordan eliminations. That's what we have done previously. We have done Gauss Jordan eliminations, but this time instead of Gauss Jordan eliminations, we are going to do row reductions basically. If you know what I mean. So if we are given a matrix, we do some row reductions here, followed by column reductions. Okay, uh, this matrix and the its equivalent matrix are known as matrix equivalent. Is that okay? So basically that means we can get the block partial identity matrix by performing row reductions to a matrix and then followed by columns reductions. We are going to do that in the tutorial. I hope I didn't confuse you. If you got confused, so just ignore what I have just said, okay? And I will do the tutorial shortly. If matrices are row equivalent, then there are also matrix equivalent. Of course, because matrix equivalence is composed or is made of row reductions followed by column reductions. So row reductions is included in matrix equivalence. Okay, so it's also matrix equivalent, and I'm sure you will see that the converse is not true. Okay, it's matrix equivalent since we can take Q to be the identity matrix, since we can take Q to be the identity matrix. Okay, but the converse is not true. The converse is not does not hold. Is not true. That means two matrices can be matrix equivalent, but not row equivalent, but not row equivalent. Is that okay? So the tutorial question says the following. I hope I will have enough space here. Let me start first. Okay. So number 9. Let's do our tutorial here. Okay. So the question is find P and Q to express H via PHQ as a block partial identity. Okay, so H is 2, 1, 1, 3 minus 1, 0, and 1, 3, 2. Okay, so if you remember in the lecture, we have here two matrices, point number 3 here, this point here, okay? Two matrices, the one in black, okay? Two matrices are matrix equivalent if and only if they can be converted to the other by a sequence of row reduction steps and followed by a sequence of column reduction steps, okay? That's one thing. The second thing is any matrix of rank K is a matrix equivalent to the m by n matrix that is all zeros except that the first K diagonal entries are 1. So I'm talking about theorem number 6 here. So that means any matrix is going to be matrix equivalent, any matrix, okay? Matrix equivalent to its canonical block partial identity, okay? So we have a matrix H, and let me call this B, Pi. This is also a matrix, okay? So these two matrices are going to be matrix equivalent. Is that okay? Because we say that any matrix is matrix equivalent to a specific block partial identity matrix, okay? So here, what we have seen here, the note in the note number 3, it says that since these two matrices are matrix equivalent, okay, we can get to this matrix, the block partial identity matrix, we can get there by performing row reductions on R and column reductions on H. We can perform row reductions steps followed by column reduction steps on H to get to the block partial identity. So you can see where we are going, okay? So this is going to be P and Q. So if we can perform row reduction steps on H from the left, okay, multiplying H from the left, all those matrices, elementary matrices multiplied together are going to give us our P, and the column reductions, if we perform column reductions on the right of H, all those elementary matrices you use to perform that column reduction, okay, will be multiplied together, will be our Q. Is that okay? So this is what we are going to do today, okay? So also before I start, if you remember, we have already done elementary reduction matrices, okay? So I'm going to fly through them quickly. If you remember what they do, if we multiply those elementary matrices from the left, it acts on the rows. From the right, it acts on the columns, okay? And we have seen plenty of them, the IJ unit matrix. We have also seen the identity matrix. We have seen a rescaling matrices. We have seen when we have two entries in the same row that the row interact, but if not, then they do not interact. We have also seen permutation matrices, okay? So I'm not going to spend too much time here to explain the mechanics of those elementary matrices multiplications. If you don't really recall, maybe you can just go and watch my previous videos, okay? The title was Mechanics of Matrix Multiplications, okay? So I'm going to use those elementary reduction matrices here straight away, okay? So what we are going to do is first step 1, if you are given a matrix like this and you ask to find P and Q via block partial identity decomposition, then you go through two main steps. Step 1, perform a row reduction, okay? Row reduction. So here is our matrix H, 2, yeah, it's true. 2, 1, 1, 3, minus 1, 0, 1, 3, 2. Okay, so we want to actually perform those rows and column reductions to get to the reduced echelon form. Is that okay? So that's what we want to do. The block partial identity is actually the reduced echelon form of the matrix. So what we are going to do here, we are going to perform Gauss eliminations first by true row reductions. Okay, then we will continue with the Jordan part. Okay, true column reductions. Okay, so since we want to reduce, okay, let me use black here. So we want to perform Gauss reduction. So we want to use the 2 in the first row to eliminate the 3 and the 1 in the second and the third row, okay? So I'm sure you know how to perform Gauss eliminations. If not, I have plenty of videos about them. Go and watch. So minus 3 over 2, 1, 0, 0, 0, 1. Okay, so if I multiply the matrix H by the this row elementary row reduction matrix, okay, in black, then it will give me the first step or the first answer or result in Gauss elimination. So the first step, so I want to use the 2 to eliminate the 3. So basically, if you remember multiplying from the left, okay, what does the elementary matrix does? So uh, the the position of minus 3 over 2 is in the second row, first column. So multiplying from the left, what does it do is it takes row 2, it multiply it by minus 3 over 2 and add it to row 1. That's what we want, Gauss method. I want to use the 2 to eliminate the 3, so I'm going to multiply row 1 by minus 3 over 2. Sorry, I said something. If you multiply with the rows, okay, from the left, it works other way around. So it will take row 1, okay, multiply it by minus 3 over 2 and add it to row 2. Okay, it's actually the column that works this way. The row works this way. Row multiplying from the left works other way around, and multiplying from the right, the column multiplications works the normal way from the left to right. Okay, so what I want here is if you multiply these two matrices, I'm going to get 2, 1, 1, 0, and minus 5 over 2, minus 3 over 2, okay? And here we will have 1, 3, and 2, okay? So now this time I want to use the 2 to cancel the 1 here. So what I'm going to do is to multiply row 1 by minus a half. Okay, so that elementary reduction matrix that will help me perform that operation is this one, 0, 1, 0. Okay, so minus a half, 0, 1. So if we multiply those two matrices together, it will give us 2, 1, 1, 0, minus 5 over 2, minus 3 over 2, and 0 here, 5 over 2, minus 3 over 2. Okay, the next step in Gauss eliminations is to use the minus 5 over 2 in row 2, okay, the leading term or the leading entry in row 2 to cancel the 5 over 2 in the row below it in the third row. Okay, so here is the elementary reduction matrix that will help me perform that operation. So 1, 0, 0, 0, 1, 0, and 0, 1, 1. Okay, if we multiply them together, we'll get the following matrix. So 2, 1, 1, we are copying row 1 and row 2. So 0, minus 5 over 2, minus 3 over 2, and here the positioning of the 1 here is a third row, second column. So it's going to use row 2 and add it to row 3. Take row 2, add it to row 3. It's not scaling row 2 because it's just 1. Okay, so this is what we want. Okay, so I want to add row 2 to row 3 to be able to cancel the 5, to eliminate the 5 over 2 in row 3. So we have 0, 0, 0. Okay, so we have 0, 0, 0 here. So we are going to stop here um yeah, for the row reduction steps. Okay, now let's continue. Okay, let's continue on the other side. Step 2. Step 2 with the column reductions. Okay, just here I wrote minus here. It should not be minus 3 over 2. It's just 3 over 2. Okay, yeah. So we will continue with the Jordan part in Gauss-Jordan elimination. So the first step here, by doing what? Column multiplication. So we are going to multiply from the right. So we have 2, 1, 1. Yeah, our last matrix here is this matrix. Okay, so we have 0 minus 5 over 2 minus 3 over 2, 0, 0, 0. Okay, and we are going to the first step in Gauss in the Jordan part of Gauss-Jordan eliminations is to turn the diagonal element into 1. Okay, so so here I'm going to use a rescaling matrix, a half. Okay, to be able, I want to turn the 2 into half, so I want to multiply row 1 by a half. So I'm going to use this matrix 0, 0, 0, 1, 0, 0, 0, 1. Okay, so here it is, we have a half, so it will give us this matrix. I hope I will have enough space. It's going to give us 1 and half. Just 1 second. Okay. So it's going to, okay, it's not going to multiply the row by a half, but the column by half. If you remember, sorry, multiplying from the right, the position of a half here is a first row, first column. So it's going to take row 1, okay, or column 1. Sorry, we are working on the column. It's going to take column 1, okay, multiply it by a half. Okay, it's going to take column 1 and multiply the column 1 by a half. Okay, so here we have 1, okay, and here 1 and 1 here, followed by 0, minus 5 over 2 minus 3 over 2, 0, 0, 0. Okay, so the next step is to, yeah, maybe instead of black I should use a different color for the column reductions. Okay, so here let me use this color to make things better. So we have we multiply by a half. Okay, so we want to work on the columns. So 0, 1, 0, 0, 0, 1. Okay, the next step is to turn that minus 5 over 2 into 1. So we are going to multiply it by minus 2 over 5. We are going to use a rescaling matrix 0, sorry, 1 0 0 0 minus 2 over 5 0 0 0 1. That's a rescaling matrix. Okay, so it should give us the following. So it's going to multiply the whole column, this whole column 2 by minus 2 over 5. Okay, so you have 1 minus 2 over 5, 1 here, and 0 1, and minus 3 over 2, 0 0 0. Okay, so the next step is to use the 1 in the in row 1, this one here, the first entry in row 1, to eliminate in column 1. Let's talk now with column, to eliminate the minus 2 over 5 in column 2 and the 1 in column 2. If you know, you know how to perform Gauss Jordan. Okay, so I'm going to multiply by this new matrix. The new matrix is I want to multiply column 1 by 2 over 5, so that if I add them together, it can eliminate the minus 2 over 5. Okay, so this is going to be the reduction matrix. 2 over 5, 0 0 1 0 0 0 1. Okay, it will give me the following matrix. So we have 1 0 1 0 1 minus 3 over 2 0 0 0. Okay, now I want to use the 1 in column 1 to eliminate the 1 in column 3. Okay, so here is going to be our new reduction matrix, minus 1. So I want to do minus 1 column 1 plus column 3. Okay, so we have 0 1 0 and 0 0 1. Okay, so this will give us the following matrix. So you will have this new matrix: 1 0 0 0 1 minus 3 over 2. Okay, 0 0 0. Okay, now the next step is to use the 1 in column 2 to eliminate the minus 3 over 2 in column 3. Okay, so I want to multiply column 2 by 3 over 2 and add it to column 3. Okay, I want to multiply column 2 by 3 over 2 and add the result to column 3. Okay, so here is going to be the reduction matrix, the elementary reduction matrix: 0 1 and 3 over 2. Okay, 0 0 1. Okay, once again, the 3 over 2, the position of the 3, this 3 over 2 here in the elementary reduction matrix is in row 2, column 3. So as you have seen in mechanics of matrix multiplications, when we talked about elementary reduction matrices, we said that it should copy. Okay, the answer should be row 2. We will take column 2, multiply it by whatever number here, so 3 over 2, and add it to column 3. That's how multiplying from the right works. So we take column 2, multiply it by the 3 over 2, and then add it to column 3. Okay, but the row works the other way around. If we multiply from the left, it will have taken row 3 and added to row 2. Is that okay? That's column, that's row. Okay, so let's continue. So we should have the following as the answer. The answer should be 1 0 0 0 1 0 0 0 0. Okay, so what we have done, as we have said in the lecture, that if we perform row reductions followed by column reduction, we will end up with a block partial identity. Okay, that's what we have seen in the lecture, because this block partial identity and the matrix H are equivalent, or matrix H is equivalent to a specific block partial identity. Okay, so to go from H to the block partial identity, we can do row reduction steps followed by column reduction steps. And since having done those steps will lead to the block partial identity, H, so we have P, H, and Q. Okay, this new matrix we have just done by doing all these steps, and the block partial identity are matrix equivalent. Okay, so as you can see, P, in this case, P is going to be equal to all these black matrices, the row, the matrices we use to perform the row reductions, but you have to be careful about how you write them down. This is the first row we have used, the second row, and the third row, row 3. When it comes to P, we write them row 3 multiplied by row 2 multiplied by row 1. Okay, so we have row 3, which is 1 0 0 0 1 0 0 1 1. Row 2 is 1 0 0 0 1 0 minus a half 0 1, and row sorry, not row, but yeah, matrix, elementary reduction matrix. 1 is going to be, I said R1, R2, R3 because that's how we call them in the lecture. It doesn't mean a row, it means, elementary reduction matrix 1, elementary reduction matrix 2, and so on. Is that okay? And the first elementary reduction matrix is 1 0 0 minus 3 over 2 1 0 0 0 1. Okay, so if you multiply them all together, you will see that P equals 1 0 0 minus 3 over 2 1 0, okay, minus 2 1 1. That is P. Okay, so let's make sure, let's check, because these operations are simple, but yet you can easily make mistakes. So let me check. Let's check, because if you make a mistake somewhere, then everything is you are doomed. Okay. So doing that will give us this. Okay. So the next one is that. Okay. Followed by this. Followed by that. Let me just double check before we can continue. Okay. Okay. So P is that. Okay. Followed by second matrix, followed by that matrix. Okay, so that's P, and Q, as you can guess, is the product of all those matrices, elementary matrices we use to perform the column reduction. So Q is going to be, so this is our R1, R2, R3, R4, and R5. Q is written as R1 is written the other way around, because I think you can guess why, because when we started with the H here, the first matrix we used is R1. Okay, so the matrix that was closer to the main matrix was main matrix H was R1, then followed by this matrix, then followed by that matrix. Okay, but when it comes to Q, the first matrix is R1, but the other way around. I'm sure you can guess. I will stop talking. So it's going to be R1, R2, R3, and R4 multiplied by R5. Okay, so the first matrix is a half 0 0 0 1 0. I hope I will have enough space. 0 0 1 multiplied by the second matrix is 1 0 0 0 minus 2 over 5 0 0 0 1. Third matrix is 1 2 over 5 0 0 1 0 0 0 1, followed by 1 0 minus 1 0 1 0 0 0 1. Then the last matrix is a 1 0 0 0 1 3 over 2, followed by 0 0 1. Okay, so if you multiply them together, you will get q, which is equal to a half. So a half 1 over 5 minus a fifth 0 minus 2 fifths minus 3 fifths 0 0 1. So that is our q. Okay, q, and that is p. So let's do small check here. So we can do a small check. You will see that if we have our matrix H. Okay, we have our matrix H. We multiply it by our P, followed by our Q here. Okay, the answer should be the block partial identity. It should be the 1 0 0 0 1 0. Okay, which is 0 0. Okay, let me draw it this way. So we have our P, which is 1 0 0 minus 3 over 2 1 0 minus 2 1 1, followed by our H, which is 2 1 1 3 minus 1 0 1 3 2, then followed by our Q, which is a half a fifth minus a fifth, followed by 0 minus 2 fifths minus 3 fifths 0 0 1. If you do these three multiplications, you will get our 1 0 0 0 1 0 0 0 0. You will get our block partial identity. Is that okay? So maybe I can just double check, and then we will stop here. Okay, that's good. Minus, that's good. That's good. I think we are okay. So I'm going to stop here. This is the end. This is a very tedious work to do, but if you know how to perform Gauss eliminations, Gauss-Jordan eliminations, and the mechanics of matrix multiplications, especially those elementary reduction matrices, you can easily find P and Q. So from now on, if you are given H, you are asked to find P and Q. What you do, perform step 1, row reductions, multiply the main matrix by the elementary reduction matrices from the left. Then you perform column reductions by multiplying the matrix by elementary row reduction matrices from the right. Is that okay? Until you get to a block partial identity. Is that okay? So we will stop here and see you in the next video.